In this video, we will study Cayley Hamilton Theorem. The theorem states that every square matrix satisfies its characteristic equation. To understand this theorem, let us solve one example. We are given a matrix A 1 3 7 4 2 3 1 2 1. We will verify whether matrix A satisfies Cayley Hamilton theorem. First, we will write its characteristic equation. That will be 1 minus lambda 3 7 4 2 minus lambda 3 1 2 1 minus lambda. Determinant of this equals 0. After expanding this determinant, we get a cubic polynomial equation lambda cube minus 4 lambda square minus 20 lambda minus 35 equals 0. According to Cayley Hamilton theorem, we know that this cubic polynomial equation is satisfied by matrix A. So we will put A in place of lambda and write A cube minus 4A squared minus 20A minus 35I equals 0. For those who do not know how to expand this determinant and get this cubic polynomial equation, I advise them to watch my previous videos on eigenvalues and eigenvectors. Let us first find out A square. That will be A square equals matrix 1 3 7 4 2 3 1 2 1 multiplied by the same matrix A 1 3 7 4 2 3 1 2 1. In this matrix multiplication, we know that we multiply the first column of the post factor by the first row of the prefactor and add this product so as to get the first element of matrix A square. That will be 20. Then we multiply the second column of the post factor matrix by the first row of the prefactor matrix and add the elements so as to get the second element of A square. That will be 23. We follow the same process of multiplying the columns of the post factor by the rows of the prefactors and adding them together to get the elements of the matrix A square. So the third element of the first row will be 23. The second row will be 15, 22, 37. Third row will be 10, 9, 14. Now in order to find A cube, we write A square into A. That will be matrix A square 20, 23, 23, 15, 22, 37, 10, 9, 14. Multiplied by matrix A 1 3 7 4 2 3 1 2 1. We will carry out matrix multiplication on the same lines and write A cube as 135 152 232 140 163 208 60 75 and 111. We will rewrite the matrices A 1 3 7 4 2 3 1 2 1, then A square equals 20 23 23 15 22 37 10 9 14, and A cube equals 135 152 232 140 163 208 60 76 and 111. Now we will verify the equation A cube minus 4A square minus 20A minus 35I equals 0 to be true. So first we will write LHS. That will be this A cube which we have matrix 135 152 232 140 163 208 60 76 111 minus 4 times matrix A square 20 23 23 15 22 37 10 9 14 minus 20 A, which is 1 3 7 4 2 3 1 2 1 minus 35 into identity matrix 1 0 0 0 1 0 0 0 1. After simplification, LHS works out to be a zero matrix that verifies this equation to be true, hence verifies Cayley Hamilton theorem. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. In the next example, we have to verify Cayley Hamilton theorem for matrix A 1 2 minus 2 minus 1 3 0 0 minus 2 1. And after verification, we have to find A inverse. First, we will write characteristic equation of matrix A, that will be determinant 1 minus lambda 2 minus 2 minus 1 3 minus lambda 0 0 minus 2 1 minus lambda equals 0. After expanding this determinant, we get a cubic polynomial equation lambda cube minus 5 lambda square plus 9 lambda minus 1 equals 0. Now, according to Cayley Hamilton theorem, this equation is satisfied by matrix A. So, in place of lambda here, we will put A and write A cube minus 5A squared plus 9A minus identity matrix I equals 0 matrix. First, we will evaluate A squared, that will be minus 1 12 minus 4 minus 4 7 2 2 minus 8 1. A cube will be A squared into A, that will be matrix minus 13 42 minus 2 minus 11 9 10 10 minus 22 minus 3. After substituting the values of A squared, A cube in this equation, we will get A cube minus 5A squared plus 9A minus I to be a zero matrix, and hence we verify that this characteristic equation is satisfied by. Now, in order to find out A inverse, we will multiply this equation throughout by A inverse. So that will be A square into A inverse minus 5A into A inverse plus 9A into A inverse minus I into A inverse will be A inverse equals 0 matrix. Now we know that A into A inverse is I. So we write A square into I, that will be A squared minus 5A plus 9I minus A inverse equals 0 matrix. Now this gives us A inverse equals A squared minus 5A plus 9I. Now in this, substituting for A, the matrix A, we get A inverse equals a matrix 3 2 6 1 1 2 2 2 5. Here we can verify that A into A inverse equals I, thereby proving this A inverse to be correct. We are given a 2 by 2 matrix A 1 2 2 2 minus 1. By using Cayley Hamilton theorem, we have to show that A raised to 8 equals 625 I. Let us first write the characteristic equation, which is determinant 1 minus lambda 2 2 minus 1 minus lambda equals 0. This will be minus 1 minus lambda into 1 plus lambda minus 4 equals 0. That will be 1 minus lambda square plus 4 equals 0, or lambda square equals 5. By Cayley Hamilton theorem, this will be A square equals 5I. So A power 4 will be 25I square, that will be I, and A power 8 will be 25 square 625 multiplied by I square, that will be I, and this is what we have to find out. In the next question, matrix A is 1 2 3 2 minus 1 4 3 1 minus 1. For this matrix A, the expression a cube plus a squared minus 18a minus 40 equals a zero matrix is true, then we have to find A inverse and matrix A power 4. Since it is given that this equation is true, we will multiply this equation by A inverse and write A squared into A inverse plus A into A inverse minus 18A into A inverse minus 40 into A inverse equals 0 matrix. Now we know that A into A inverse is identity matrix I. So A square into I will be A squared. A into I will be A. Minus 18 into I will be minus 18I minus 40 A inverse equals 0 matrix. This we write as 40 into A inverse equals A squared plus A minus 18I. So A inverse will be 1 by 40 times the expression A square plus A minus 18I. That will be equal to 1 by 40 into value of this expression works out to be a matrix minus 3, 5, 11, 14, minus 10, 2, 5, 5, minus 5. So this will be matrix A inverse. Now in order to find A power 4, we will multiply this whole expression by A. That will give us A power 4 plus A cube minus 18A squared minus 40A equals 0 matrix. That will be A power 4 equals 40A plus 18A squared minus A. Now by using matrix A in place of this A, we will get matrix A power 4 as 248, 101, 218, 272, 109, 50, 104, 98, 204. So this will be matrix A power 4. In the next question, we have to find characteristic equation of the matrix A 2 1 1 0 1 0 1 1 2, and after that we have to find the matrix represented by the expression a raised to 8 minus 5 a raised to 7 plus 7 a raised to 6 minus 3 a raised to 5 plus a raised to 4 minus 5a cube plus 8a square minus 2a plus I. We start by writing the characteristic equation of matrix A. After expansion of this determinant, we will get a cubic polynomial equation lambda cube minus 5 lambda square plus 7 lambda minus 3. We know that this equation is satisfied by the matrix A. Now we will divide after replacing lambda in place of A in this expression, that is lambda raised to 8 minus 5 lambda raised to 7 plus 7 lambda raised to 6 minus 3 lambda raised to 5 plus lambda raised to 4 minus 5 lambda cube plus 8 lambda square minus 2 lambda plus in place of I we will write 1. We will divide this by this expression lambda cube minus 5 lambda square plus 7 lambda minus 3. To start, we will divide this lambda raised to 8 by lambda cube. That will give us quotient lambda raised to 5. Now lambda raised to 5 multiplied by lambda cube will be lambda raised to 8. Lambda raised to 5 multiplied by minus 5 lambda square will be minus 5 lambda raised to 7. Lambda raised to 5 multiplied by 7 lambda will be 7 lambda raised to 6. Lambda raised to 5 multiplied by minus 3 will be minus 3 lambda raised to 5. We will change the signs. This will be minus, plus, minus, plus. So after subtraction we get 0. Next we will pull down this lambda raised to 4, then minus 5 lambda cube plus 8 lambda square minus 2 lambda plus this one, and now we will divide this lambda raised to 4 by this lambda cube. That will give us quotient as lambda. Now we will multiply this whole expression by lambda. and write lambda into lambda cube lambda raised to 4 lambda into minus 5 lambda square minus 5 lambda cube lambda into 7 lambda, that will be 7 lambda square, lambda into minus 3 lambda. Next we will change the signs. Lambda raised to 4 minus lambda raised to 4 will be 0. This will also be 0. 8 lambda square minus 7 lambda square will be lambda square. 3 lambda minus 2 lambda will be lambda, and plus this one. Now since the degree of the divisor is 3 and that of the remainder is 2, the division process will stop here, and this will be remainder R and this will be quotient Q. Now we will write this long division in terms of dividend equals divisor into quotient plus remainder, which is the division algorithm that we know. So this will become, in terms of the matrix A, the dividend which is equals the divisor after putting A in place of lambda multiplied by the quotient which is A raised to 5 plus A plus the remainder A squared plus A plus I, writing I in place of 1. But the expansion of this determinant, which is this, is nothing but 0. So therefore this divisor will be 0. So the whole expression of the dividend becomes only A square plus A plus I. We can find A square, that works out to be by matrix multiplication or self multiplication 5 4 4 0 1 0 4 4 5. Therefore the value of A squared plus A plus I will be, after putting the values of A square and A and I, matrix 8 5 5 0 3 0 5 5 8, and this will be the matrix represented by this expression here. So this is the required expression. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.